We're starting a new topic. There's a bunch of new stuff to do. We have about a month worth of class, and then you never have to do calculus again. And I know that puts a smile on many of your faces. All right, so let's see. So we talked about functions, then we talked about derivatives, and we talked about exponential and logarithmic functions. Now we're going to go back to sort of derivatives, but going in the other direction. So we learned how if you take a function, you can take the derivative of it, and that tells you how the function is changing, and increasing and decreasing, and rates and all of that. Now, we're going to go backwards and do antiderivatives. So antiderivatives give you different information about a function, and they're related through something called the fundamental theorem of calculus, which we may or may not get into, but certainly not today. So antiderivatives are, as I said, working backwards. They are more difficult to do by far. It is very easy in general to take a derivative. You've learned how to take derivatives. They're really not that hard. You can make mistakes, but you see that the mechanics of it is not that difficult. However, going backwards is much harder. So it's sort of like you can smash something, but it's very hard to put it back together again. So, because many times you take the derivative of something simple and you end up with something long and complicated, like when we had the quotient rule. So if you started with the quotient rule to go back and figure out what the original function was, is not so easy. So antiderivatives, as I said, the other direction will be more difficult. But I have faith that you are a bunch of smart young men and women, and you will be able to do it. So, okay. So the symbol for antiderivative that we're going to use is the integral symbol. This symbol means the integral of f of x. An integral and antiderivative, as far as we're concerned for now, we sort of use interchangeably. So we could also say it's the antiderivative. So now let's figure some of these out. So say I gave you something very simple. Okay, by the way, what does that dx mean? Well, dx is part of the anti-differentiation. Just the way you had dy dx when you took a derivative, you're going to have something dx when you do an antiderivative. First, it says that we're doing it with respect to x. And second is it has a meaning, which will be clearer when we talk about more stuff next week. So for now, just it's always in there when you start with the integral, and it goes away when you finish with the integral. So for example, if I said, what's the integral of 5? You say to yourself, well, so we have an answer, 5. So what was the original function? I heard somebody say it. 5x, right. So we must have started with 5x. Right? Because the derivative of 5x is 5, so the antiderivative of 5 would be 5x, going the other direction. However, we have a small problem. It could also be 5x plus 1. Because the derivative of 5x plus 1 is also 5. It could be 5x plus 2. It could be 5x plus pi. It could be 5x plus a billion, minus a billion. That constant, when you take the derivative of that constant, you get 0. So there could be any constant attached to 5x. So we write plus c, where c is the constant. And unless I give you more information, you have to leave it that way. And this is called an indefinite integral. It's indefinite because we don't know what c is. I can give you more information. So let's I tell you that the integral of 5 dx equals blah, and I tell you that f at 0 is 4. Okay? And I say this is f of x. So we say, all right, well, that equals 5x plus a constant. And since f of 0 is 4, I now know that 4 is 5 times 0 plus the constant. 5 times 0 is 0, so the constant must be 4. Therefore, the equation is 5x plus 4. So if I give you a little additional information, you can often figure out what the constant is. Okay? How do we feel about this so far? It's pretty easy, right? Of course, I'm going to give you something harder than 5. What if I gave you 5x? You say, well, what would it be? It must be something like 5x squared. Right? Because if we take the derivative of x squared, we get 2x. So if we had 5x squared, well, let's try 5x squared. The problem is, what's the derivative of 5x squared? It's 10x. So, I'm sorry? 10x, right. So it's 10x, not 5x. So we'd have to divide this by 2. That 10x divided by 2 is 5x. That would get us back where we started, plus some constant. What if I gave you the integral of 7x? Well, it would be 7x squared would be 14x. So again, we have to divide by 2. That 2 seems to be important. You see why we have the 2 in there? Because now if you take the derivative back, you end up with twice as much. Because when you took the derivative of x squared, you got 2x. And here we only really want to have x. What if I had the integral of 7x to the third dx? You say, well, let's see what happens to that 7x to the fourth. And if I take the derivative of that, I get the 4 goes in front. So I have 28x cubed, but I only want to have 7, so I have to divide by 4. So it looks like I'm dividing by whatever that power is. And we are. And that's the first integral rule that we're going to want. So, rule number 1. Well, we actually have 2 rules. So we had one where we just had a constant. That became the constant times x plus different constant, okay? So when we had the integral of 5, it just became 5x. Now, what if I have kx dx? Well, the k doesn't seem to matter. I'm sorry, not kx, kx is the n. So the constant, just like with derivatives, the constant just sort of ceases to stay there. This becomes, you raise the power by 1, because then when you take the derivative, you go back. And you divide by whatever that power is. So in a derivative, you bring the power in front, multiplying it, and subtract 1. So the antiderivative, you return the power, adding 1, and divide. And that way they undo each other. Because let's take the derivative of x to the n plus 1. That f of x is x to the n plus 1 over n plus 1 plus a constant, so that's what I have there, forgetting the k part. And the derivative, bring the power in front, reduce the power by 1. And the derivative of the constant is 0, so these cancel, and you get x to the n, which is what we were doing over there. So if I had integral of x to the 8th, you add 1 to the 8 and you get 9. And you divide by the 9 plus a constant. Remember, you always have to have that plus c. Don't forget it. Because the derivative of any constant is 0. And if I had the derivative of 3x to the 8th, that's 3x to the 9th over 9 plus c. So many people, including me, when you see an integral with a constant in it, so if you saw, say, the integral of 6x to the 5th, they put the 6 outside. That's very useful for when you get to messier integrals. Because what will happen is the thing in the inside, called the integrand, can get very complicated. So pulling the constant out can often just make it a little easier to work with. They're the same thing. Now what would that be? Well, that would be 6 times x to the 6 over 6 plus a constant. So that would just be x to the 6 plus a constant. Okay? How do we feel about these so far? It's not very hard, right? You literally just add 1 to the power, divide by the new power. Of course, we could make a chain of these. So if we want to find that integral, this should be just as straightforward as differentiating, just going the other way. So this would be 3x to the 5 over 5 minus 5x to the 3 over 3 plus 2x to the 2 over 2 plus 3x plus a constant. So each time, take 4, you add 1 to the power, divide by the new power. Squared, so you add 1 to the power, divide by the new power. 2x, that's x to the 1, so it becomes x to the 2 over 2. Those 2's are going to cancel. The integral of the constant, remember, is the constant times x, and then you have plus c. How do you feel about these so far? You feel okay? Nothing too challenging? Okay. It does get trickier. The integration can get very complicated, but we only do very straightforward versions of it in this class. We only have 2 or 3 types because I don't know how many integrals you're going to run into in your life. And at some point it just becomes an exercise in sadism. For me, that's the best part. What's the integral of the square root of x? Well, the square root of x is x to the 1/2, right? So you could rewrite that as x to the 1/2. And then the antiderivative would be x to the 3/2 or 3/2 plus a constant. Then dividing by a fraction, you flip and multiply to get 2/3 x to the 3/2 plus constant. So far, so good? Okay. What if I gave you 1 over x? That's x to the negative 1, isn't it? But when you add 1 to the negative 1, what do you get? And then you have to divide by 0. Doesn't make any sense, right? Because you get x to the 0 over 0. So what is it? Ah, you seem to have forgotten something. What's the derivative of natural log? The derivative of natural log is 1 over x. So the antiderivative of 1 over x, the integral of 1 over x, is natural log. But we make it absolute value because it's possible this is a negative value here, but you can't take the log as a negative number. So just in case you throw in the absolute value. Again, that's the kind of thing that you're going to have to just sort of know. But the odds that we do something with that are very small. But it's not just natural log of x, it's natural log of absolute value of x. So let's make sure everyone's on their game. All right. Take a minute, see if you figure that out. All right, it's long enough. So some of these are easier than others. Integral of x to the 3rd, is x to the 4th over 4. And for x squared, it's x to the 3rd over 3. And then for 8x, it's x to the 2 over 2, which you could simplify to 4x squared plus 3 times x. And that's minus 4 on the absolute value of x. And what are we going to do with the 6 over the square root of x? Well, that's 6 times x to the negative 1/2. So we would make this 6x to the positive 1/2 over 1/2 plus c. Notice, we don't write a plus c for each of the terms. You can just do one big plus c at the end. Since you haven't figured out what c is, it doesn't really matter until you actually calculate it. This could be simplified a bit. You could make that x to the 4th over 4 plus 11x cubed over 3 plus 4x squared plus 3x minus 4 ln of x plus 12 radical x plus c. If you wanted, and by the way, since you remember your log rules, you could make that the log of x to the 4th if you wanted. However, it's usually more convenient not to have the power. So first, look at how we do on that one. Were we able to do that? Yes? No? Maybe? Men's amends? Get trouble with the last term, right? The square root term. Right, let's practice a couple more of those, just to make sure. You have to be comfortable with the powers. Suppose we had the integral of 1 over x cubed plus 1 over the cube root of x. If we wanted to do that, say, well, before we do the integral, let's rewrite this just so we can use our power rule. That 1 over x cubed is x to the negative 3. And cube root of x is x to the 1/3. So 1 over the cube root of x is x to the negative 1/3 dx. And now you just have to practice adding 1. So the integral of x to the negative 3 is x to the negative 2 divided by negative 2. And x to the negative 1/3, negative 1/3 plus 1 is positive 2/3. So that's x to the 2/3 over 2/3. Remember when you were in 5th grade and you said, when am I going to use fractions? There you go. Now you finally are using this stuff. Long-term payoff. Plus c. And then if you wanted to rewrite this, there's no need to, but if you wanted to, this is 1 over x squared, so it would be negative 1 over 2x squared, because the x to the negative 2 is 1 over x squared. And then plus 3 over 2 times the cube root of x squared, plus c. Now, why would I want to do that? Just so it's easier to look at, if I need to work with it or plug in numbers or something like that. Otherwise, just leave it alone. There's nothing special about one or the other. And as opposed to derivatives, we don't really integrate again. There are a couple of applications where that shows up, mostly in physics. But we really just, you integrate once and you're done. Right? All right? Let's give another just to make sure he has the idea, just to make sure you're comfortable with playing with powers. Got it? Okay. Many of you are nodding. That's a good sign. All right, I would rewrite this as x to the negative 5 minus x to the negative 1/2. Leave the 1 over x alone. And then this is x to the negative 1/5. And then take the integral. So the integral of x to the negative 5 is x to the negative 4 over negative 4. The integral of x to the negative 1/2 is x to the positive 1/2 over 1/2, divided by 1/2 multiplied by 2. The integral of 1 over x is log of x, absolute value of x. And then x to the negative 1/5 would be x to the positive 4/5 over 4/5. plus c. And I said you could rewrite that. That would be negative 1 over 4x to the fourth minus 2 radical x plus log the opposite of x plus 5 times the fifth root of x to the fourth plus c. So far, so good? Okay. One last type. We did polynomials, square roots, log. We forgetting anything? Oh yeah. Forgetting one. What's the integral of e to the x? Well, what's the derivative of e to the x? E to the x. What do you think the antiderivative of e to the x is? E to the x. That's not too hard. And if you throw a constant up here, well, when you took the derivative, you would multiply by that constant. So you take the antiderivative, you're going to divide by the constant. Because you're sort of working the chain rule backwards. So the integral of e to the 5x is e to the 5x over 5 plus a constant. Well, if I want to do the integral of e to the x minus e to the minus x. Well, the integral of e to the x is e to the x. The integral of e to the minus x is e to the minus x over minus 1, which is just negative e to the minus x. So the minus minus becomes plus. Whenever you do an antiderivative, if you're not sure if you got it right, take the derivative. Derivative of e to the x is e to the x. Derivative of e to the minus x is minus e to the x, which is exactly what we have here, because the derivative of the constant is 0. So the integrals of e's are pretty easy. Okay? I mean, I can say what's integral of pi x? Pi scares lots of people because they go, there must be something different. No, it's just e to the pi x over pi. And there's things you can do with integrals. So, first of all, we only did for one little problem, about how you find c. That you usually have something called an initial condition. And then what do you do with integrals? You can do all sorts of things with integrals. Integrals are very useful for finding the area under a curve, or for adding things up, for doing a sum. In fact, the integral symbol, the s, is an elongated s, and it just stands for sum. We're going to get into more. So as I said, unfortunately, I know you're going to be sad. I have to do a short class today, and I have to go grade exams. So we'll see all of you on Monday.